Hi guys, so today we're going to look at exponential growth and decay. So exponential functions you probably saw a little bit in Algebra 1. We're going to do some exponential stuff here at the beginning of the unit, and then we're also going to look at logs, which are basically the inverse of an exponential function. So to start, your basic growth and decay equation is right here. It's that a times b to the x. It's important to take notice of the fact that a and b are not, you cannot just multiply those two values together. Okay, they are written that way for a reason. The b is the only one of those numbers that has the exponent on it. The a does not. Okay, so if this is the parent function, okay, then that a value is going to be 1. Okay, if that a value is greater than 1, that's your initial amount when we talk about growth and decay. That's also going to be your y-intercept, because again, that's your starting point. So the parent functions is what we're going to look at first. Again, the parent function is when a is 1, so our parent function is just going to look like the base raised to the x power. Now what's interesting about this function is that it's going to have a different shape depending on what that base is. Okay? If that base is greater than 1, then this graph is going to show growth. The reason for that is just some of the points that this graph will go through. So for example, one of the points this is going to go through is 0, 1, because anything raised to the 0 power is 1. Another point this graph is going to go through is 1, comma, whatever the base is, because anything to the first power is itself. So 1, comma, the base will be another point. And then another point that's going to be on this graph is -1 and the reciprocal of the base, because a negative exponent is going to flip that value. So my graph is going to go through those points, which is going to create this sort of a shape. And if you think back to that activity we did in class with the M&Ms, that also helps you kind of see how these growth and decay functions look. So our decay function, again, similar points. It's still going to go through 0, 1. It's still going to go through 1, comma, the base. And it's still going to go through -1, the reciprocal of the base. But because my base is less than 1, my base is going to be smaller than my y-intercept. And the reciprocal, because it would be flipped, will be larger than the y-intercept. So your graph is going to go in the opposite direction and show decay. Now both of these graphs have a horizontal asymptote at y equals 0. All right, because again, even though this is going to shrink and grow, it's not actually going to get to 0 because it's not going to completely disappear. All right, so we're going to look at a couple examples here. The first thing we're going to determine is just whether or not these are showing growth or decay, and then we're going to do a graph with at least 3 points on it. So this first one is going to be growth, because again, the base here is greater than 1. So the points this would go through, it is going to go through 0, 1. It's going to go through 1, comma, 3, because that's my base. And it's going to go through -1, 1 over 3, because that is the reciprocal. So it's going to go through 0, 1, 1, 3, and -1, 1/3. So there's my graph, and it has, again, that horizontal asymptote at y equals 0. All right, looking at B, again, 3/4, that would be decay. Okay, that would go through 0, 1, 1 the base, and -1 the reciprocal of the base. And again, that reciprocal is now larger than the y-intercept. So your graph's going to go in this direction. All right, number 2, even though there is a 2, that's kind of that a value there, okay? You cannot multiply that 2 with that 3/4. You have to keep them separate, okay? The 3/4 is that growth. Well, it's not really the rate, but it's showing us what the rate is, okay? That's showing us this is still decay, because the base is still less than 1. Okay, that 2 does not change the fact that this is growth or decay. What that 2 is going to change is our y-intercept. So our y-intercept for this one is actually going to be 2, because that's my initial amount, that's my starting amount. So this graph is going to go through 0, 2. It's also going to go through 1, and it's not going to go through 3/4, it's going to go to 3/4 times 2, which would be 3 over 2. And then this graph is going to go through -1, and then I would take the reciprocal times 2. So 4/3 times 2, which is 8/3, which is above the intercept. So there's my graph. So again, that number in front does not affect if it's growth or decay, but it does change your y-intercept, which in turn changes your other points. when we talk about transformations, that's very similar to your vertical stretch. Okay, then let's look at D. Again, even though this is a fraction, this is still showing growth because the value is still greater than 1. So this is going to go through 0, 1, 1 5/4, and -1, the reciprocal. So there is my graph. All right, so what we're going to look at here is just some ways to rewrite these in different forms. Now, we'll look at these again when we look at some word problems with growth and decay, but I just want to see the basic example here. This is 2 to the 2x. Okay? Another way to rewrite 2 to the 2x using exponent properties, if you have multiplication in the exponent, that is a power to a power.
How'd it go?
So then it's 2 squared to the x, because again, power to a power, you would multiply those exponents. So then I could just rewrite this. This would be y equals 4 to the x. And now it's just in this form, so it might be a little bit easier to graph if you didn't have a calculator, or just a different way to graph it. So again, your one here would be your a value. So it's not shown, but that's what it would be. So now we're going to look at some exponential growth and decay word problems. So this is really the actual application of this, very similar to what you guys saw in that activity that we did in class. So on this first one, it says the value of a car in thousands of dollars can be approximated by this model. T is the number of years since the car was new. Okay. So the first thing we need to determine is whether or not this model is showing growth or decay. And the way we can tell that is based off of our base. So our base is less than 1, so this is showing decay, right? It also makes sense for the problem that a car is going to, the value is going to decrease as you continue to drive it. So since it's decay, we know we are using this model equation up here. So what we need to do now is actually find what that percent increase or decrease is. 0.92 or 92% is not that change, because remember, in that equation, 0.92 is the 1 minus r, and r is actually what I'm looking for. So if 1 minus r is 0.92, r is actually 0.08, which as a percent would be 8%. So that is an 8% decrease. The last thing is we're going to estimate when the value of the car will be $9,600. So the first thing we need to determine, 9,600, is that going to replace y or is that going to replace t? That is going to replace y. We also need to be careful that it says that the value of the car is listed in thousands of dollars. So we're not going to use 9,600, we're actually going to use 9.6, because 9.6 in terms of thousands of dollars would be 9,600. Again, a clue there, because our equation is 31. Okay, the car does not cost $31, the car costs $31,000. So it keeps it in line with that. And then we're just going to solve for t. Now, we cannot solve for this algebraically quite yet, just because we have not gone over logs yet. So I'm going to show you guys how to solve this algebraically using the calculator to kind of model this problem. All right, so there's two ways that you could do this. One option is that you can graph the left portion of the equal sign as y1. You can graph the right portion as y2, and you can find the intersection, as long as you make sure your window is appropriate to see that intersection. But your calculators, the Casio calculators you guys are using, actually make this a little bit easier. So let's look at that. Okay, so here's my function. So the first thing I'm going to do is I'm going to change my window, okay, because I want to make sure, there we go, to make sure it's going to be easier to see. So x is my time in years, okay, so I don't need a negative time. I need my time to at least be large enough for the duration of the car. I'm just going to go ahead and make it 20 so we can see a lot of it. All right. Y-min, again, is the value of the car. So 0, I don't really need a negative value of the car. That's never going to happen, because, again, that exponential function has that asymptote. Because even though the car is going to decrease in value, it's never going to be a negative amount. And then the maximum value here needs to be at least 31, because that was the starting point. Okay, so now I'm going to go ahead and graph this. So there is my model. Okay, so now we can use this to find any information that we want using gsolve. So what I'm going to do is I'm going to go to gsolve, and then I'm going to go to over to see some more choices, and then I see this ycal and xcal option. So what these are, these allow you to find y values or find x values. Okay, so it's what you enter is going to be the opposite of what's listed. So if I go to ycal, I'm going to enter an x. Okay, if I go to, whoops, sorry about that. If I go to xcal, I'm going to enter a y value, and that's what I'm doing here, because it's going to calculate the x. That's what I'm trying to find. I'm solving for x. So what I know is that y is 9.6. And then it tells me the x value that goes with it, which is about 14 years. Okay, so it's going to take approximately 14 years for that car to become valued at $9,600. All right, so now let's go ahead and look at another example. So this time it doesn't give us the equation. We need to write the equation from the information. So the population of a city was 1.04 million. In the next 14 years, the population increased by 2.05%. So this is growth. So we're going to use our growth equation. So this is going to be 1.04 is my starting amount, and then it's going to be 1 plus that rate. Okay, 2.05% as a decimal is 0.0205. Add 1 to that, so it's 1.0205 to the t. All right. If I want to estimate the city's population in 2008, because it says that time is the number of years past, a number of years after 2000, then the time that I'm going to plug in then, I'm going to use 8. Okay, plug that in and get your value. You can do that either on your calculator or you can do that in Run Matrix. And then to solve for C, then I'm going to evaluate when y is equal to 1.3, I'm going to solve for x. So again, this is when I would use xcal on my calculator. So go ahead and try those, and then I will put your answers up here in a second. All right, so if you had a chance to find those values in your calculator, then you would have gotten that when in 2008 your population would have been 1.22 million. And then on that last question, you would have solved for x, and you would have found that in the year 2011. So your x value would have been 11, so in approximately year 2011 you would have gotten that. All right, so now what we're going to do is we're going to use those exponent rules, very similar to what we did in the second example, to rewrite functions into this growth model. And what that helps us do is that helps us figure out what that actual rate is. Because based on this equation right now, it's hard to see what our rate is. So I'm going to rewrite it. This is going to be 2 to the 1/3 to the x power. Then from here, I can actually evaluate 2 to the 1/3 using a calculator. We know that's the cube root of 2, but because we're actually looking for a rate here, we do want to actually use that decimal so we can actually calculate what that is. So if I actually evaluate this, I would get that 2 to the 1/3 is 1.26. So in that model, this would be 1 plus 0.26 to the x. So this is obviously showing growth because it's greater than 1, and specifically that percent would be 26. All right, so then on the next one, same concept. I would rewrite it as 0.5 to the 1/12, and that's raised to the x. I would evaluate 0.5 to the 1/12 using a calculator, so that gives me 0.94 to the x, which then I can rewrite. This is going to show decay because it's less than 1. And this shows me that it is a 6% decay. All right, and then example 6, if you feel pretty comfortable, pause the video, try this one on your own. All right, so this is somewhat trying to model half-life for you guys. So this is 0.5 to the 1/13. That's raised to the x. The 13th root of 0.5 I can actually evaluate with a calculator. So this is going to become 0.9481 to the x. So I can rewrite that. This is going to show decay because it's less than 1. And then that as a percent would be 5.19%. All right, the last thing we're going to look at is a common application for exponential growth and decay, and that is compound interest. So what it means for interest to compound, it means that's when your interest gets added back into your account. The more frequently the interest is added into your account, then you're going to be able to get interest on the interest. So the more frequently it happens, the better it is for you. So we're going to look at a very basic example here just to kind of see what happens. I'm going to say $100 and 10% interest. Now the odds of you finding 10% interest, especially with just $100, not very likely, but it makes it really easy to at least see our percentages here. So looking at if it's compounded yearly, what that means after year 1, you would have $100 that you started with plus 10%. 10% of 100 is just $10. So at the end of year 1, you would have $110. Okay, well then year 2, you would start with $110. You would get 10% interest on that amount, which is now $11. So you're getting an extra $1 of interest now that you have that interest added back in. Okay, so now at year 3, we would take $121. We would get 10% of that, which is $12.10. Again, I'm now getting $2.10 more than year 1 on my interest because that interest is being added back in. So now I have $133.10. So again, the more often that interest is added back in, the better off that's going to be for you. So to show if it's compounded quarterly, what's actually happening here. So if I look at the first quarter, okay, I'm going to start with $100. Okay, and then I'm going to take 10% of my interest, which is $10, but because it's the first quarter, I'm only going to get a fourth of that interest, okay, which we know is going to be $2.50. So I'm going to have $102.50 at the end of the first quarter. Okay, so now when I get to the second quarter, which is halfway through the year, okay, I'm going to take that 102.5. I'm going to take 10% of that. And I'm going to divide that by 4 because, again, we're just looking at a quarter. And when I add that back in, I now have $105.06. So I'm already 6 cents over what I would have just been if I just did halfway. Okay, so again, quarter 3, I would take that $105.06. I would take 10% of that. I would divide it by 4 because it's a quarter, and that would put me at $107. And then finally for the end of quarter 4, which is also the end of the year, okay, I would take the amount that I have, 10% of that, divide it by 4, and that would put me at $110.38. Now, quarter 4, that is the same as the end of year 1. So if you notice, when it's compounded quarterly, it's not a big difference, but it's a difference. So you've made an extra 38 cents just by the fact that your interest was compounded differently. Okay. Again, if you have larger amounts of money, higher interest rates, compounding can make a bigger deal. So it is something definitely to consider when we're talking about these numbers. So the way this formula works, we have to consider P as principal, that's your starting amount. Our annual interest rate, we always write as a decimal, so if it's 5%, it would be 0.05. Our time, we need to consider it in years because it's an annual interest rate, and we're also looking at the number of times your interest is compounded in years. So if you're looking at 18 months, you need to use that as 1.5 years. All right, and then N is the number of times that it's compounded in a year. Okay, so if your interest is compounded daily, then your N would be 365. If it's compounded quarterly, your N would be 4. Okay, if it's compounded semi-annually, then it would be 2. All right, so let's look at our last example here. So 2 accounts, all right? Let's go ahead and look at the first account. So you have $10,000. Okay. It is compounded daily. My rate is 0.0165. Since it's daily, we're going to use 365. All right, and then 5 years, we would plug in 5. All right, account number 2, $10,000. Different rate. This time it is 0.0168, but this time it is compounded quarterly. So 4 is going to go in both of those places. We're looking after 5 years. And again, at this point, we can just plug this straight into our calculator to get our values. So if you plug this in, account number 1, you're going to end up with $10,000, $10,859.97. In account number 2, you are going to end up with $10,874.38. So even though the other account was compounded more frequently, the higher interest rate makes a bigger difference, and our second account is going to give us more money after 5 years. All right, so we're going to continue to look at exponential functions, and we'll also look at logs in the rest of this unit.